There are some occasions when a polynomial can fit into multiple factoring categories or multiple factoring patterns. In those situations, we want to make sure that we understand that when we factor, the answers may not look identical to one another, but still follow those tenets that we're looking for. We're looking to try to simplify as much as possible. We're looking to simplify difference of squares and difference of cubes. We're looking to see if farther down the line there's maybe a perfect square trinomial or something we could use the AC method on. As long as we're following all of that, we're making sure we're looking as we go. If we take alternative routes, that's really not a major concern for us. An example of a polynomial that you can use multiple routes to factor is something like x to the sixth, y to the sixth. Anything that falls to the sixth power does fall into the category of squares and cubes. So you could consider this a difference of squares, or you could consider this a difference of cubes. We're going to look at it both ways and see how we end up with slightly different answers depending on the track we take. So we're going to start with looking at it as a difference of squares. If you think of this polynomial as a difference of squares, this would be x to the third and x to the third. This would be y to the third and y to the third. So we have our two binomials, x cubed plus y cubed, x cubed minus y cubed. Thinking through our other factoring strategies, this is a difference of cubes, and this one is a sum of cubes. So we can continue our factoring from there. Factoring this sum of cubes, using our factoring pattern for the sum of cubes, we get x plus y, x squared minus xy plus y squared. So remember, we want this symbol to match the symbol from the original binomial, and then this symbol to be the opposite. So we have that. And then we come over to the difference of cubes, and we're going to do the exact same thing except just flipping those two signs. X squared plus xy plus y squared. We don't have techniques for either of these two polynomials. You might want to try to AC it, but it doesn't work because you can't find something that multiplies together to make one and adds together to make one. You can't perfect square trinomial it because even though it starts with a perfect square and ends with a perfect square, the middle term of each of them is not twice the product of those two outer ones. So this is it. This is the best we can do given the circumstances. That is the factored version of x to the sixth, y to the sixth. But what if we approached this not as a difference of squares from the beginning, but rather as a difference of cubes? So looking at the same exact example, we're going to think of x to the sixth as a cube of x squared. And we're going to think of y to the sixth as a cube of y squared. And those are the individual terms that we're going to use in the difference of cubes formula. So we'll start with x squared minus y squared, and then square the x, multiply the two roots together, and then square the y squared, and there's our factored form. But popping out of there is this binomial right here, which can also be treated as a difference of squares. So we can go one step farther and say x minus y, x plus y, followed by that trinomial that came out of the difference of cubes. We can't go any farther on this one for the exact same reason that we couldn't go farther on the previous example, and we definitely can't go farther here. But comparing these two answers to each other elicits an interesting outcome. If you look at this answer right here, and then you compare that to this answer right here, you'll notice that x plus y appears in both of them. So we have an x plus y there and an x plus y and x minus y both appear. So we have x minus y and x plus y. That means that everything that's left over after those two must be equivalent to one another. We started in the same place. We started with x to the sixth minus y to the sixth, and regardless of the route that we took. So what does that mean for us? Well, if we're looking at these polynomials, we see a leftover portion right here, and a leftover portion right here. And then we see the leftover portion of this one right here. While we didn't think there was any other way to factor this particular polynomial, there actually is. Because of the equivalence of these two results, we can say that x to the fourth, oh, I'm sorry, this was supposed to be fourth. My mistake. We can say that those raised to the fourth power, I'm sorry, x to the fourth plus x squared plus y to the fourth, we can say that that's equivalent to those two leftover portions from the difference of squares. So that polynomial must be equivalent to x squared minus xy plus y squared times x squared plus xy plus y squared. So something that didn't even fall into our normal factoring patterns, our regular factoring patterns, has a factorization, and we're able to get through to it through the factorization of x to the sixth minus y to the sixth. We knew they had to be equivalent. So even though we took two different routes at the beginning, we knew that they end up having to be equivalent because they started in the same place. And despite the one little mistake that I made right here, and this was supposed to be a 4 from the jump, we can see how these terms would get created in this polynomial by doing some of the multiplications that would appear over there.